Okay, picking back up with example 2, we've taken our antiderivative using tabular integration by parts. A wonderful, wonderful shortcut. But now we have to finish with the fundamental theorem. And please do remember we still have that limit out in front. So with the fundamental theorem, if we were to work this all out, we'd get negative t e to the negative t minus e to the negative t minus, and then we'd get, plugging in a 1, you'd get negative 1 e to the negative 1 minus e to the negative 1. And really just want to call your attention to the fact that if this limit of that first parenthesis is going to arrive at a real number, our integral will converge and our series will then converge. And by way of comparison, if we're working this limit out and the first parenthesis goes to infinity or negative infinity, officially doesn't exist as a real number, then we get divergence. Maybe to help you out a little bit as you finish this limit up, you certainly could think of that first parenthesis as bringing that reciprocal down. You don't have to do this, but it certainly can be helpful. If you want to distribute this negative in, you could say plus, and here's a 1 over e plus 1 over e. That negative gets distributed to both. But let's review something together. If we were to take a look, just going off to the side real quickly, for the graph of e to the x, as we go off towards infinity, of course, we're going to be arriving at infinity. So I guess what I'm trying to do is come back over here and maybe just touch on this expression right over here. As t goes to infinity, e to the infinity goes to infinity. 1 over infinity is going to go to 0. So, what I've highlighted in yellow, 1 over e to the t, that thing's going to 0. So things are looking better for the moment. You can think, wow, now I just have to worry about this other component, negative t over e to the t. And if you were to look at that limit, guys, you're going to be getting negative infinity over infinity. We have to do L'Hopital. Very good, guys. Very good. So I just want to call attention. You can even do a little scratch work off to the side here. You can say, well, wow, what if I had negative t all over e to the t? With L'Hopital, guys, take the derivative of the top, and you'd get negative 1. Down below, you'd still have e to the t. And e to the t is going to infinity. What's negative 1 all over infinity going towards? 0. What are we seeing? Coming back over here, both parts of the first parenthesis are going to 0. So, in other words, this first parenthesis is just going to wipe out. 1 over e plus 1 over e is 2 over e. That integral that we just worked out converges. So, more or less what we just saw is going from 1 to infinity of x all over e to the x dx. You work that out, you're going to get 2 over e. What you now know is this series converges or diverges. What do you think? Converges by the integral test. And I can't stress enough the very important fact that the series does not converge to 2 over e. A lot of kids want to write that. They'll say, yeah, that series does converge, and you add everything up and you get 2 over e. No, that's what the integral converges to. The integral, in this case, would be representing net area, right? And this summation, that summation isn't representing area. You're looking at very different ideas. All the same, the behavior of the integral, the infinite integral, the fact that it converges means that that infinite sum would converge also. Okay? So that's it for the integral test. And now we're going to go to something that honestly is just delightful. It's the P series. The P series, P could actually represent a power. Sometimes kids are wondering why it's called a P series. And what does the P series look like? Well, it's 1 over n to the P, and you're going to have an infinite sum from 1 to infinity. So what does that really look like? Well, if n is equal to 1, you get 1 over 1 to the P, which is just a 1. Let n equal 2, you get 1 over 2 to the P. Let n equal 3, and likewise you get 1 over 3 to the P. Add that up forever, and this is what you get. Now, if you recognize that, and again, P is a positive real number here. Here's the amazing thing. This is just delightful. This is just wonderful. When you have a P series, when you've got 1 over n to the P in summation, if your power is bigger than 1, your series converges, game over, that's all. It's justified, you're good to go. By way of comparison, if your power down below is equal to 1, or if it's going to be less than 1, then your series will diverge. Plain and simple. Guys, it will take you a second or a fraction of a second to look at these problems and know whether you get convergence or divergence. Here's what I'm talking about. Look at 3a. Tell me what the power is. What's P? 2. It's a P series. You've got n raised up to a power. What's happening? Converges. Because if that power is bigger than 1, you get convergence. That's what the P series tells you. You look at this next one and you think 1 over radical n. Here, maybe this will help you out. Square root's really the 1/2 power, isn't it? Just as the cube root would be the 1/3 power, and the fourth root would be the 1/4 power, and so on. In other words, P is equal to 1/2. What happens? Diverges. Done. Last, you could say, well, wait a minute. Your power isn't a whole number. Your power is 3/2. You could also write it as 1.5 if you'd like. That's going to be converging. Why? Because if your power is bigger than 1, you converge. End of story. Yep, you have to have a 1 up on top, but in the homework, you're also going to see things like this. 2 all over 1.5, n to the 1.5. That's still considered a P series because you could just factor a 2 out, and then it's 2 multiplied to the P series.
It's like E times.
If it's E out in front, E is a constant also. Oh, down below, you could factor out a 1 over E, right? So that's still going to be a P series. Good questions.